Hello guys, how's it going? Mike coming back at you here with another video on discrete mathematics. In the previous video, we talked about the inverse, the converse, and the contrapositive of a conditional statement. We mentioned that some of those were logically equivalent to each other. We'll be seeing some of those examples in this video here. And then we talked about the biconditional statement, what it's logically equivalent to. And then we talked about a fairly common phrase that's used in mathematics, specifically in textbooks, the necessary and sufficient condition. So in this video, I'm just going to get a little bit of practice with stating the inverse, the converse, and the contrapositive of a conditional statement. We're going to see how some things are logically equivalent, and then we're going to see a truth table example where a biconditional is involved. So kicking it off with our practice with inverse, converse, and contrapositive. Here is a sentence. Find the inverse, converse, and contrapositive of the following sentence. If the Bills lead by 20 points at the end of the game, then the Bills have won. So take a couple minutes, perhaps, maybe not even that long. Try to come up with what the inverse, the converse, and the contrapositive of this sentence is. Take portions of this sentence, label them as P and Q. It shouldn't be too hard to figure out what things should be labeled as P and Q. Just look at the form for the conditional statement. If P, then Q. And then just look at what the formula, in quotes, for the converse, the inverse, and the contrapositive are. And you should be able to figure out pretty easily what are those three things for this particular sentence. So pause the video now, try to figure out what each of those three things are, and then press play and see if you got it right. All right, so let's see what you got. First up, the inverse. Again, this is where we take the not of P and Q, and it's not P implies not Q. So the inverse is if the Bills do not lead by 20 points at the end of the game, then the Bills have not won. Or you could say the Bills have lost. Next up is the converse. Once again, converse is you're just switching the locations of P and Q. So now it's Q implies P, not P implies Q. So the converse is if the Bills have won, then the Bills lead by 20 points at the end of the game. Last one, the contrapositive. You're essentially doing both the inverse and the converse. You're starting off with P implies Q. You're then doing the inverse, not P implies not Q. And then you're switching the places of those guys. So you have not Q implies not P. So for this particular sentence, the contrapositive is if the Bills have not won, then the Bills do not lead by 20 points at the end of the game. And thinking back to what we said in the previous video of how the inverse and the converse are logically equivalent, and the statement itself and the contrapositive are logically equivalent, but say the inverse and the contrapositive are not logical equivalents. You can kind of see how that makes sense now with this one particular sentence. If the Bills lead by 20 points at the end of the game, then the Bills have won. If you compare that to the inverse, if the Bills do not lead by 20 points at the end of the game, then the Bills have not won. That's not necessarily the same as the sentence that we were given to start with. because the Bills can still lead, just not by 20 points, and they can still win. If you compare the contrapositive to the statement that we were handed, if the Bills have not won, then the Bills do not lead by 20 points at the end of the game. We can see that that does make the same sense as the sentence that we were given. If the Bills have not won, then at the end of the game, they do not have the lead, and therefore they do not lead by 20 points. So just the thought of why are the inverse and converse logical equivalents also a statement and its contrapositive being logically equivalents, but those things between them are not. Seeing this sentence maybe makes that a little bit more clear. Now, what we're going to do is we're actually going to go through a truth table, and we're going to show how a conditional statement and its contrapositive are logically equivalent. We're going to show that we're going to come up with the same set of truth values for the conditional and the contrapositive. So we have our 4 rows, each of our 4 possible combinations of truth values for P and Q. So filling in the columns in this table, it's really straightforward to find the columns for not P and not Q, just switching the truth values. Now we have our conditional. We're looking at these 2 rows, these 2 columns. A true implying a true gives me a true. True implying a false gives me a false. And then in each of the last 2 rows, P is false, which means your conditional is true. That gets us our 5th column there. Now we are working with the middle 2 columns to find the truth values for the final column here. Not Q implies not P. And be careful about the order that you look at these trues or falses, because the order does matter. We have a false implying a false, which is going to be a true. We have a true implying a false, which is false. We have a false implying a true, which is true. Now we have a true implying a true, which is true. And just as a small reminder, we're coming up with these values just based on our knowledge of a conditional statement and how and the cases when it's true or false. We're not just assuming it based on the values from the previous column and what we know about a conditional statement and its contrapositive. We're verifying this thing on its own. But we can see that we do indeed come up with the same set of truth values. T, F, T, and T going down. Therefore, these things are indeed logically equivalent. One more problem here, just going to do a truth table involving a biconditional here. So we are going to show the truth table for not P or R if and only if Q and R. This is the truth table that we're going to come down to in the end. So we have 8 rows, because 8 possible combinations of truth values for P, Q, and R. Next column to fill in, pardon me, is the column for not P. Again, very straightforward, very easy. 4 F's followed by 4 T's. Now we have not P or R. So we're going to take the disjunction of these 2 columns here. A false or a true implies a true. False or a false gives me a false. False or a true gives me a true. False or a false gives me a false. And then in each of our last 4 rows, not P is always true. So these are all going to be trues. So there is our 5th column being filled in. For our next column, Q and R, so we're taking the conjunction of those 2 columns there. When they're both true, the conjunction is true. Otherwise, it's false. So true and a true gives me a true. True and a false. False and a true. False and a false. T, F, F, F for the first 4 rows. And then we're going to go, we're going to have the same sequence of values. True, false, false, false. So there's our 6th column here. Now we have the last column to fill in. Not P or R, if and only if Q and R. Now, refreshing ourselves from the previous video, the biconditional is only true when both P and Q are the same truth value. If they're both true, then the biconditional is true. If they're both false, then the biconditional is true. If they don't have the same truth value, then the biconditional is false. So I'm using the biconditional on our 5th and 6th columns here. So a true if and only if a true gives me a true. A false if and only if a false gives me a true. A true if and only if a false gives me a false. False if and only if a false gives me a true. A true if and only if a true gives me a true. And then for each of the last 3 rows, we have a true if and only if a false. So these are all F's. They're all falses. So that is our truth table. We've shown the truth table for this logical form, not P or R, if and only if Q and R. So these were just a few sample problems, seeing the inverse, the converse, and the contrapositive, verifying that a conditional statement and its contrapositive are logical equivalents of each other, and then just seeing one more truth table, now including a biconditional. If you have any questions or comments, be sure to drop them in the comment section below. Otherwise, until the next video, take it easy, guys.